Benjamin Feng is not only our first speaker today, but also our first returning speaker ever. Normally I try to make a joke in the introduction, but this time all I want to say is thank you, Benjamin, for your courage and your effort. His talk today is the first talk that we are hosting meant to introduce newcomers to the Zig programming language to a systems programming concept. The title is What's a Memory Allocator Anyway? And Benjamin, the stream is yours.
Hi, thanks for the introduction, Loris, and it's good to be back. And let's get started with our talk. So as Loris has just mentioned, my talk is going to be on memory allocator, specifically manual memory allocation. And to understand what is a memory allocator, we need to understand why is a memory allocator. And that's actually a pretty good question because let's take a look at what the Zig compiler will provide for us. So this is just a very simple simple function that I wrote up real quick. All it does is it takes two variables, a start and an end, and it goes and it sums up everything in the middle. And how that looks in the actual compiler is that we will be provided a segment of memory. At the very top is going to be some function metadata, specifically the return address, but it may include some other things in there. And then we have the two variables that we're passing in. Let's pretend that this is a very dumb compiler and we're not using registers. So we're going to reserve start and end as part of the memory that we need in our execution. And then we also need the result and the current. And the result is the data that we return back, and the current is sort of a temporary space. And this is all the memory that we need for running this function. Every time you invoke this function, it will go. The compiler will go ahead and just reserve all this space for you. And the nice thing about this is you don't have to think about it. As a general programmer, I never have to really think about any of this stuff because it's all automatic. Like stack memory is handled by the compiler and it's handled really well because it has very simple semantics. And you know exactly what's going to happen. It's very fast at allocating because you literally just advance a pointer a couple of steps so that you have enough memory. And you also have, because everything is predetermined by the compiler will literally just write a bunch of offsets in the middle of your code. It doesn't have to calculate any of that. It's just purely based on what's in the stack right now. So everything is fast, and cleanup is just the opposite. You just unwind a single pointer. So everything's fast, and everything is basically trivial to the compiler. So why isn't this good enough for all programs? Why do we need a concept of manual memory allocation? Like there are some fundamental limitations on how you can use the stack. And the first big problem is you have a fixed amount of total memory. And this, depending on which operating system you run, this may be a little bit more flexible into how much fixed total memory you have. But generally speaking, you're never going to be able to allocate gigabytes on the stack. That's just something that the operating system will not allow you to do for pretty good reasons. So even if you are able to expand the stack, you're still having a limit as to this is not the total memory. If you want 16 gigabytes, you need some other way of accessing that memory. You also have a problem with fixed sizes because the compiler needs to know exactly how big the memory space is for every variable in your program. And so they must be fixed. And if you need any sort of dynamic allocation, for instance, if you don't know the size of something or you need to like expand the size at some point, this is not really possible on a stack. I mean, it's a little bit possible in some operating system, like Linux gets you allocate, which allows you to expand stack variables. Zig actually doesn't let you do that because it was found to be unsound and buggy. So we can't actually do that in Zig, and we don't want to do that in Zig. A workaround here is you can allocate a maximum buffer size, and that way you can sort of have a maximum size that you can allocate towards. But if that maximum size is not big enough to handle, say, user inputs, then your program can't actually operate on that. And the last problem is lifetimes. Because of the way that the stack is structured, the lifetime of this variable only exists inside this function call, or in Zig, it's actually inside of a specific block. And that's kind of that's not a problem if you're using values directly. So if you're always copying around the start value, the end value, that's not a problem because you're just passing around values. As soon as you use pointers, pointers into stack memory can easily be hanging references. And that's the same type of bug as a use after free bug. And that leads to memory corruption and all sorts of really bad things. And because you don't have control over your lifetime, you can't build something like a linked list on a stack and return it. So these are all sort of very big limitations with how the compiler works with memory. And it's, in general, you want to use stack memory as much as possible. But if you run into these limitations, you can't really leverage the stack anymore. So what do? Well, let's come up with the simplest allocation strategy. The easiest way to do manual memory allocation is by making someone else do it. So like the operating system gives us a way to ask for more memory, and we'll just see what that looks like. And this is sort of a dumbed down version of the page allocator that exists in the Zig standard library. It's a bit more complicated than that, but this is sort of the meat that I want to focus on. And in an allocation, what we do is we'll just go ahead and request a memory from the operating system. And in a POSIX system, that's memory map or mmap. And upon freeing it, we just call memory unmap. And this is very simple and almost trivial. And you might be wondering, hey, what's the catch? Well, like, why can't we use this? Why is this not actually recommended by Zig? And there's sort of a problem going on with this. And for one thing, system calls are very slow, like in orders of magnitude slower than a typical function execution even. And this is because of a number of things that have to relating with memory protection and interrupts and jumping into kernel space. All that stuff is very slow to execute, and it trashes how the CPU wants to view memory. So if you're doing many of these allocations, this is actually going to be a massive slow point in your program. If you're allocating, for instance, a dozen different nodes for your linked list, every time you ask the operating system for a node, it's going to be super slow, and it's not a good way of running things. And the other problem is that it is very wasteful. You may have seen this align forward and wondering what the hell is going on here. And that's because the operating system has a very stripped down view of memory. It does not understand memory in bytes, because if it was trying to figure out memory in bytes, it'd be very slow and wasteful. So the operating system actually has a view of memory in pages. And a page is typically 4 kilobytes for most modern operating systems, and it's 64 kilobytes on WebAssembly. And that means that whenever you ask for memory, you have to ask for a page or a multiple of a page. So if you're asking for 8 bytes for your linked list, well, you can't. You have to ask for 4 kilobytes. And then your linked list will use 4 kilobytes of that 8 bytes of that 4 kilobytes, and you're wasting 3.99 kilobytes every time you're asking for memory. So this is really bad in two different, very catastrophic ways. So now the flip side you may be asking is, if it's so bad, why do you want to use the operating system at all? And the answer is the operating system actually has all the memory that's available. When you run your program, you typically don't map all the memory that you need directly into your program immediately. So you need some way of asking the operating system for more memory. Now, you can start with all of the memory mapped, but that means that your memory usage is governed by how much maximum memory you have at all times. So if at a maximum you need 1 gigabyte of memory, you map 1 gigabyte when you start out, and that's not ideal, because if most of the time you only need like maybe 10 megabytes, then that extra memory is wasteful. It may not start up, and it's just all sorts of I can't think of the word. Not optimal, unoptimal. There we go. So that's why you want to ask the operating system for more memory. And this is sort of the basis of most of the allocators, but it's also not what most people use as allocators directly, because again, it could be very wasteful. So instead of just like trusting someone else, how about we actually implement one? This way we have a little bit more control of what's going on. So what is the simplest allocation that we can, or what is the simplest algorithm that we can do? And that's called a bump allocator. And it's in Zig, we provide a bump allocator in the form of a fixed buffer allocator. We use a fixed buffer to back a single allocator. And the allocator, all it does is it stores an extra extra field called the end index. And as you allocate, you bump the end index upwards, and you create these segments of memory at the bottom of the buffer, or at the top, depending on your strategy. But as you allocate more memory, you just bump the pointer upwards a bit. And that way, you actually track how much free space you have left. And also, you track how much memory you have previously consumed. So there are a number of downsides to this, but the big benefit is that this is very simple. It's very simple and it's very fast. So because allocating memory is just a couple of additions, comparison, plus and that's really it. You get very fast allocation, and you get a little bit more control over the lifetime. It's not fully controlled because depending on where you put the buff, so your lifetime is now controlled by where your buffer lives as opposed to where your variable lives. And that gives it a little bit more flexibility. You can move the buffer from this current stack upwards into the stack. That gives it a bit longer lifetime, or you can even move it out to the global space. It's still not like complete control over where it is, but it's a lot better. So you won't accidentally like start pointing into free memory that's no longer part of the mapped stack. But there are still major problems with this. Probably the biggest problem that we have is that your memory is still fixed. We call it the fixed buffer allocator because your buffer is fixed. We can't expand it in any way. So once you run out of free space, then there's nothing you can do, and you just sort of hold your hand and be like, well, we're out of memory. And this is even worse because you can't actually free memory. Now, we can sort of wiggle our way around and say, oh, you can free memory. You can free the last allocated memory. It's like in this instance, we can free the 32 byte. Because it's at the last spot and we can detect that. But we can't actually free the 8 bytes at the very beginning or the 4 bytes in the middle. There's no data structure to store that because all we're storing is an end index. So free is very limited, and the only way to properly free is to do a first in, first out approach, which when you work with manual memory management, it's very hard to guarantee that. So in most respects, you could treat it as you can't free memory, and any free memory that you actually get is sort of an optimization and not an actual like something that you can depend on. So yeah, we can free the last allocation. But the other thing that we can do is we can reset the entire buffer because because we're storing the end pointer, we can just be like, oh, the end pointer, let's point it at the beginning. So even though we can't really free individual memory and trying to free it with last allocation is brittle, we can actually reset the entirety. If we know that this the data that's inside this buffer is no longer being used, we can just go ahead and flush it and start from scratch. And that's actually very fast, and that's a valid way of reusing your buffer space. But so let's skip and let's ignore the fact that you can't really free memory right now, and let's talk about fixed total memory. Personally, this is kind of a bigger blocker for me because like there are often times I don't know how much memory I need. If I'm writing parsing code, I can just keep guessing until I get the right number of free memory, but that seems very not fun. So what can we do to lift this idea of a fixed total memory? Like, what if we could have a bumped allocator with expandable memory? So instead of having one fixed buffer, how about we have expandable buffers? So here we just basically fill up individual buffers, and every time we fill up a buffer, we'll just go ahead and we'll create a new buffer. And if we fill that up, we'll create a new buffer. This way we have unlimited memory as long as we can create buffers. And we still have the bump allocator style where we're just moving up the pointer, and that's still going to be really fast. Now you may be asking, well, where are the buffers coming from? And the answer is this type of allocator requires a backing allocator. So something else needs to be providing the actual memory that's happening. And just so happens we just explored one of the allocators, and that's the operating system. So we'll have Tux here give us all our memory for us. And this way, we have the capability of having expandable memory while mitigating most of the downsides of hitting the operating system and asking for more memory. So for instance, if you start allocating a bunch of linked lists inside this new allocator, which we're going to call Arena Allocator, we're actually just going to be bumping up the memory here, and we very rarely will need to ask the operating system for more memory. So this is a lot more performant, and it sort of mixes two allocators together and gets the best characteristics of both. And again, it's very fast allocation because it's still bumping. You have expandable memory, which is good. And the other great thing is that you have fully controlled manual lifetimes. Previously, with our fixed buffer, we're still governed by where the buffer lives. But now, since we're actually asking the operating system for memory, we can control when that free happens. So whenever you're done with it, you can't free individual memory. That's still not allowed, but you can free all of the memory that we have requested, and that just goes directly back into the operating system. And not being able to free individual memory, that sounds like a sort of a limitation, and it is. But however, there are many types of problems that you can actually get away with not freeing individual memory. And there are two big categories of algorithms that freeing individual memory may not be that great. The first one is if you have lots of allocations for one lifetime, freeing individual memory is not actually that useful. If you think, if you've used malloc before in the past and you build a linked list and then you have to free that linked list, you have to go through and iterate through each individual node to figure out where to actually go and free it. So if you have like 100 nodes, you have to do 100 different freeing. You have to free 100 different nodes individually. It would be nice if we could free them all at once, and you can with an arena. You stick all of those nodes inside of a single arena. You put it at the top of the tree, or the list in this case, and then you can just go ahead and free all of them at once. And that's a much faster operation because you're not iterating through a bunch of nodes, and it's one operation because you have basically one chunk of memory to store all of that. The other and slightly more fuzzy approach is that if you don't have to free individual memory, if your lifetime is known and you can get away with a little bit of temporary garbage space, then you don't need to free individual memory, and you still have the easy lifetime of the arena. So in this case, for instance, a web request, you can structure your arena in a way where you create the arena at the beginning of a request, and you free the memory at the end of the request, and everything in between is automatically cleaned up for you. And this while it's not ideal because if your request actually allocates like megs of memory and then tries to free them, it's still going to be hanging around until the request is finished. But it also protects you from leaking memory outward in case you didn't free it. So this is, if you have a known lifetime, applying an arena can make your system a lot more resilient to like manual memory management holes that you may have forgotten. So this is actually a very popular strategy in Zig. We do it all the time, and the standard library does it for like parsing. It does it for other type of handling, and it's a surprisingly flexible strategy. However, there's still a problem with not being able to free memory. I'm not saying that it doesn't happen because it always does. So what do we do about freeing memory? Like, how do we make this memory allocation general purpose? And the easy solution is we just create some metadata and stick it in a free list. And how that works is looking at this code here. Let's skip ahead to the free algorithm, and instead of returning the memory anywhere, we're just going to create a linked list node out of the memory, and we'll append it to, or prepend it. I'm sorry, prepend it into our little free list tree here, and then whenever we need to allocate new memory, we can go ahead and we find a matching size. And this way, we are creating a linked list of these nodes, and each of these nodes can be of a different size, and then we can basically find it again if we need more. And if we can't find a matching size, that means, oh, we don't have the existing memory. We're going to have to actually go and create new memory. And this does work. This does work. You can free memory. You have some way of storing free memory, and that's really our goal, right? Well, there are major problems with this approach. And for the first thing is that allocations have a limited size. In order for us to free memory, we need to be able to store it in a linked list. So we need at least a next pointer. And a next pointer has a minimum size of 8 bytes on a typical 64-bit machine. And so whenever you allocate 1 byte, we have to bump that up to at least 8 bytes in order to free memory. Or we can just go ahead and never be able to free anything less than 8 bytes. There's a trade-off there, but the point is that we have some issues with that. This is also very slow. In order to allocate memory here, we all of a sudden converted this from a constant time to a linear time, because we're actually scanning through the entire list in order to find free memory. That's O of 1, and that's going to be slow. That's not ideal. It's possible for it to be the memory that you're looking for is in the front of the list, but there's no guarantees there. And there's also a problem with fragmentation. Now, this gets into other considerations, but like, say if you allocate 8 bytes, and then you allocate 1 byte, and then you allocate 7 bytes. Ignoring the fact that we can't really free those things, that 1 byte of allocation is actually segmenting your memory and preventing it from being used ideally. So if you free these chunks of memory, now you have an 8, 1, and 7 chunks, even though it could be 16 bytes. And that leads to horrible degradation of performance the longer your program is running. And there's no such thing as defragmenting your memory, because you have pointers that go everywhere and you can't really track them down. So this becomes a huge concern. And this is just, even though this works for like our general purpose, this is not ideal. And I almost don't want to use this because it's so bad. So how do we fix some of these problems? And so the answer is, what if we introduce a concept of size buckets? Now we have different lists for different sizes. And the big thing that happens here is that if you have a different size if you have a different list for different size, the first access into that list is guaranteed to be the right size. So instead of traversing through the entire list of things, you only need to find one value. You only need to find the first value. If it exists in the list, then that's good. That's what you're looking for. If it doesn't exist, well, it's empty. You don't have to look through the entire list, and that's really good. And for fragmentation, it's a bit more mitigated. Let's put it that way. We no longer have a 1 byte chunk or 7 byte chunks or whatever. Everything's a fixed size. So for something like a 1 byte, we'll just bump it up to 8 bytes. For something like 10 bytes of requested memory, we'll bump it up to 16 bytes. And that way we have our nice limited trees, as well as reducing the contention of memory fragmentation. It's not completely gone, but it's a lot more mitigated, because like, I'm pretty sure that we can reuse 8 bytes or 16 bytes or 32 bytes. I have a hard time of thinking about reusing something like a 13 byte chunk. So we can definitely reuse these. It's just that it's still not ideal, because you still get some fragmentation. So it's not all gone. And then the limitation is allocations have a fixed size. That actually is a little bit of a problem, because now allocations, you can have wasted memory in allocations. If you're asking for 10 bytes and you get 16 bytes, that's 6 bytes wasted. That's not a lot at a small scale, but it can accrue up to pretty large numbers. So any other problems with this approach? And the answer is it's a little bit subtle, but the bigger problem here is we have cache pressure. And modern CPUs are very fast. They're so fast that they're like hundreds of times faster than memory. So whenever you run out of cache, you have a cache miss, then you have to actually access random memory, and that's really slow. And the way that we structure any sort of linked lists, you almost guarantee to run into cache problems. And that's because of the way that the linked lists are written, where your nodes can jump all over the place in memory. There's actually no structure whatsoever in the naive approach, and it's very hard to actually keep it structured. And when you're allocating single bits of memory at a time, this is not really a problem. I mean, it is a problem because you have cache pressure, but it's guaranteed to be a cache miss anyway if you're allocating sporadically. Like this data structure is not going to be in the cache. But if you're allocating very quickly, like say in a loop, you need to allocate 10 different free nodes, then every access to this node is going to be a cache miss, can be a cache miss because it's jumping all over the place in memory. And that's really bad. There are ways to mitigate that by, instead of allocating 10 nodes by themselves, you can allocate 10 nodes at a time. And that's a strategy called object pooling. And that works really well, but that's outside of the outside of the allocator. What if we can do something to the allocator to make this type of behavior better? Because this is actually a pretty common use case. We don't want to always be like, oh, hey, you're using my allocator. Well, you should probably pool everything together. Because, yeah, you probably should, because it's a better approach by default. But a lot of people may not be thinking about this. And also, like, even if you are thinking about this, there are times where you don't necessarily know the total number that you want to pull in, and pulling together it may either give you too little, which you need to expand memory, which is slow again, or you allocate too much, in which case you're taking up a lot more memory than you need. So is there anything that we can do to make our memory more cache friendly? And yes, we can, because we can actually, instead of using a linked list, we should be using arrays. Arrays are much faster and much friendlier to the CPU nowadays. And this gets into slab allocator. And a slab is sort of harkens back to our arena allocator, whereas we, instead of having these buffers, they're now called slabs. And each slab is segmented in a way that the entire slab has the same amount of memory. And this has a very nice characteristic that linear memory, or amounts of memory that are allocated next to each other, have a much higher chance of being actually next to each other. So in our case, if we try to allocate four nodes from the first size, they're going to plug in right at the four bright areas. And two of them are literally right next to each other, and they're all very close by. And slab allocator will guarantee that whenever you allocate memory, it's going to be probably pretty close to each other. We can't guarantee that, because obviously we can't guarantee how the memory can be freed, but this has a much higher likelihood of being next to each other than using a linked list, because of the way the algorithm is structured. And also, we still have the fixed sizing, so that we can access different sizes pretty easily. And this actually fixes most of our problems with what we had before. Allocation still has the fixed size. That's sort of a problem. We're no longer very slow. We don't actually have traditional memory fragmentation anymore, because our memory will be fixed sizes. So there's no such thing as memory fragmentation in our case, because everything that's on the 8-byte slab will be guaranteed to be 8 bytes. You can't fragment that. And we got rid of a lot of the cache pressure. So this sounds like this is great. So what's the catch here? And there's a catch, and that's the meta storage. Depending on how you store the metadata, it can cause problems. And basically, if you want to store the metadata outside of the slabs, that's a possibility. But now you have an external set of memory that you need to manage, and that has its own characteristics. You can run out of external memory, and that would be really bad. And also, it's another external memory, which means it's another cache problem. If you put it internally inside the slab, that actually takes up a spot in your slab. So like, for instance, it takes up at least one element in your slab. So if you have if your slab is 1 kilobyte of blocks at a time, then your metadata will actually take up an entire kilobyte, even though you only need 10 bytes there. So that is not ideal, and that's pretty wasteful. So there are, again, more mitigation strategies, and that's probably going far beyond sort of the content that I can cover here. But there's actually a lot more going on that I sort of glossed over. So we have all these other ideas that we probably need to solve, because allocators need to sort of understand these things. Alignment's a big contention, especially with the modern day. A lot of things require memory alignment for things like SIMD and GPU work. If their memory is not aligned, you actually can't access it, and alignment requires its own little algorithm to calculate everything correctly. C compatibility, we don't actually care about a lot of that in Zig because Zig allocate and free carries the metadata around. C, when you free memory in C, it doesn't actually, you don't pass the size back. So that size needs to be accessed somehow by the memory allocator. So that idea needs to, if you want malloc and free compatibility, you need to start worrying about additional ways of how to store your data. There's also like threading, everything that I've talked about, just ignored concept of threads. If you, the naive way is using locks, but that's actually really slow. So a more modern way is that you actually have different affinity for memory. So different threads will get different blocks of data. So like a slab will live only on one thread that's thread local at that point. Other ideas, memory efficiency, we talked about corruption. If you accidentally do a buffer overrun, do you write garbage into the middle of your memory, into your metadata, which is really bad? Or do you accidentally write to some data, which is a lot less bad, potentially? Or do you write to additional buffer, which is actually could be okay? That could be a way to work around buffer overruns by just allocating a lot more data. And there's also debugging and binary size. So there's a lot of these things that has to happen in any sort of allocators. And the point is that it is impossible to make an allocator to do everything well. And even though we call it a general purpose allocator, there's not actually one true general purpose allocator. That's why we have lots and lots of different algorithms. And I personally believe that Zig is in a great spot for allocation because of the way that we structured it. So there is no default allocator. We have to make decisions around all of these things. And that I believe that that's a good thing. And even if we get a general purpose allocator, which we don't right now because writing one is hard. But even if we do, I'm hoping that because allocation can be tricky and you can have different ideas of what you want out of your allocator, that we can still keep this idea of, oh, okay, we're going to use an arena here. We can use general purpose here. We can use a different general purpose here because we need some debugging thing to do. And mixing and matching allocators in Zig is a lot easier than almost every other language. Like C has malloc, everyone uses malloc. That means you can't really swap out. And C++ has new and delete, and almost everything has a default. And because Zig doesn't have a default, I think it's in a better spot in terms of allowing you to manually manage all of this memory. And that's really the meat of what I have. I can be found sometimes streaming on Twitch. And I've written my own little general purpose allocator for WebAssembly. It is targeted towards WebAssembly, so I made the trade-offs of I don't care about threading, and I'm trying to squeeze it down as small as possible. And I am trying to convert it into a slab allocator, and I guess we'll see how well that goes. Thank you very much for having me on.
Thank you, Benjamin. Let's switch to the Q&A now then. Just a reminder to the people, to the viewers, to ask a question to Benjamin, remember to tag me in the chat message so that I don't miss it. You can send a message on Twitch chat, you can send a message on Discord, or also the Zig IRC channel on Freenode. So I'll be monitoring all these places. Let's switch to the Q&A now. Okay, so while people start thinking questions, if they have any, let's start with a few basic questions. So how are you, Benjamin? How do you feel? This is your second talk, right? So was it easier than the first time? Yeah, how do you feel in general?
I'm feeling okay. Definitely a little bit more nervous because this topic is something that I'm less familiar with. But yeah, I'm enjoying myself so far. I hope that everyone else is too.
Yeah, I've seen quite a few positive messages on Twitch, at least. So I think people appreciate it. And I remember before the show started, there were a few people like Timmy and somebody else that were interested in knowing more about allocators in Zig in particular, because as you pointed out, it's a bit of a Zig is in a bit of a peculiar situation when it comes to allocators. So let's see a couple of questions that we have already. I'm curious about memory alignment. When using an allocator, do I need to care about memory alignment for a block of memory that I give to the user, or alignment of headers that the allocator use?
Yeah, so in Zig, I sort of had a dumbed down version of this method signature there, but we actually care about the alignment that the user is requesting. So the alignment of the headers and the metadata, it doesn't matter outside of your allocator. So you can put that anywhere you want to, provided that your allocator is able to access them. But for the consumer, they need the memory to be aligned. And so typically the limit in at least C land is 16-bit aligned or 16-byte aligned. Sorry. And that allows for 128-bit memory, which goes well into SIMD registers. But that's sort of the implicit alignment for malloc. For Zig, we actually pass around the requested alignment, and you have to match the requested alignment whenever you give back. The alternative approach is if you can't actually give alignment like that, you can just return out of memory. And that's a valid strategy. And now I would argue that your memory allocator is not quite general purpose, but maybe that's a good enough trade-off. And again, that speaks to how Zig works, that you're allowed to make these trade-offs. If you don't need any sort of special alignment, it's easier to do just standard 4-bit alignment. And if that's a disadvantage that you're comfortable with, you can actually write allocators like that. Whereas in C, malloc has to align to at least, I think, 16 bytes on a x86 system nowadays. Could be even higher now with AVX instructions, but like Zig gives us the flexibility of treating that alignment how you want to.
We have another question. Could we plug in something like oh, now that I think about it, I don't know how to pronounce the name. Jemalloc, Jemalloc.
Jemalloc?
Jemalloc,
Yeah. So in Zig, we actually have a way to expose a C allocator, and you just link a libc into it, and you can link any malloc compatible layer into Zig, and that'll work actually. That works quite well. The problem is that again, C malloc is only 16-bit aligned. If you need more alignment, C malloc won't provide that for you. But if you need a general purpose allocator right now, the official approach is that yeah, you can just link in whatever C allocator you want to, and it should just work.
Okay, so the solution that you're proposing is so one way would be just to link against that by selecting the right library. But there was a second part of the question, so just to cover everything, it would still be possible to like create a Zig jemalloc project on GitHub where you link the C library and provide your own like Zig Zig-like interface, right, to it.
Mm-hmm. Oh, you don't need to provide the Zig-like interface. That's actually the standard library provides a Zig-like interface on top of any C malloc. So you don't need to write a special one for that. You just pull in, I think it's std.heap.c allocator, and it'll just work as long as you linked in a libc.
Perfect.
And jemalloc is one of them. I don't know if that's the standard, but it's definitely becoming the standard of a lot of different systems. So you have to consult whatever your libc is, whatever malloc it uses. But yeah, you can just the shims are already provided for you.
Mm-hmm. So which allocators don't have the fixed size problem?
So most allocators don't have a fixed size problem. The fixed buffer allocator is the one that is fixed. And it really depends on sort of the strategy that you're providing. Recognizing that having a fixed size is probably not the best approach. Most allocators will not have a fixed size. The reason that fixed buffer allocator is fixed is because it's simple and it's fast. Those are two very good qualities that you want. And if you're able to make the trade-off there, that's why you want. If you don't care about expanding memory, you should almost always want to use fixed buffer because it's just faster.
Mm-hmm.
But if you need any sort of expanding memory or you need a free memory, then that's when you want to venture out and use a different one. So there's only one that's really fixed because there's no reason to use a fixed buffer allocator otherwise, because the fixed buffer allocator is probably the fastest that you'll ever get.
Yeah, I remember using the fixed buffer allocator a bunch of times, I think while I was writing tests for my Redis client library. And so since I was controlling the input, I knew how much memory I needed, and this was really the fastest way of like writing the test, making work, and also have the tests run fast. So that's maybe a bit of a peculiar use case, but that's one that fits well. So there is another question that I think Timmy wanted everybody to answer, but I'm going to pose it to you so that also you can have an opportunity of contributing. And he's asking, why is something like jmalloc considered very fast even while being a general purpose allocator? Is the speed relative or something else?
I mean, the speed is always going to be relative. Using jmalloc will never be as fast as using a specific one for a specific algorithm. So you can always tune whatever algorithm you have to have a faster characteristic. However, for being a general purpose allocator, jmalloc is very fast. And you almost want to use jmalloc as the backing allocator for a lot of different things. Like for instance, if you're allocating dozens of linked list nodes, it's probably faster to pre-allocate that at once instead of allocating each individual one. And to do that, you'll just allocate an array of 24 of these nodes, and that's one allocation call. And that's guaranteed to be fast on almost any system. If you allocate one at a time, it's probably going to be slower, but it's going to be a lot less slower on something like jmalloc as opposed to something like the free list one that I built myself, which is horrendous. So yes, there are trade-offs, and yes, jmalloc isn't ideal for probably any specific problem, but it's good enough for almost every problem, and that's why it's used so heavily. And generally, you want a general purpose algorithm that makes these trade-offs and has like 90% performance for almost every non-degenerate case you can throw at it. And that's what makes it general purpose. It's never going to be great. It's never going to be the best, and it's never going to be perfect, but it may be good enough that it doesn't matter.
Mm-hmm. So there's a comment from Andrew related to jmalloc, where he says that he would be interested in seeing a port of the entire library rather than trying to use it directly.
Yeah, that's a possibility. jmalloc is non-trivial. Looking at the code size of that, it's pretty big, and there's a lot of different concepts going on. I mean, it's a project of like decades of experience. Most of the concepts I presented is just one or two of them. jmalloc probably uses like a dozen or 24 different strategies that actually works together. So yes, that's definitely something that we would like to do, but it's also probably very complicated and might take a full-time staff to work on properly, at least to get it off the road. So it's possible, but it's complicated for a good reason. And also, because it's so complicated, I refuse to use it in WebAssembly because I think the output size of jmalloc was like 500 kilobytes. And that's a little bit ridiculous. So I don't personally use it because I write a lot of stuff in WebAssembly, and forcing to download half a megabyte of binary is just a little bit ridiculous. So again, trade-offs. It's fast. It's pretty performant. It takes a lot of binary space for it to actually work.
So this is a question from me. I remember reading recently that there was a new allocator strategy that there was a research paper that I think made the news a while ago, where they were adopting a strategy where they would try to allocate let's say that you have 2 pages. They would try to allocate non-overlapping areas of memory of the 2 pages, and then they would be able to merge the 2 pages together, right? Have you had any experience with that or opinions?
I've watched the talk on it, and it's interesting. The thing that they're doing is that when you allocate arbitrary memory, it's very easy for your memory to be fragmented to hell. And one of the strategies to how to defragment this is by merging pages. If you have 2 different pages and they don't have overlapping used memory, most operating system allows you to just glue the 2 pages together. They still look like they're separate, but underneath the covers in a virtual page memory thing, it's actually one continuous block of memory. And this allows you to merge pages and reclaim a lot of the fragmentation. I don't know how any of that works. I don't really work with operating systems. This requires a lot of in-depth knowledge of how each individual operating system works with these pages and how to actually merge them together. Their solution is literally to just randomize which page it's on, and that works better than like 90% of every other solution, including linear scan. So somehow randomizing the data makes the random fragments easier to compress. So it's interesting. It sounds impressive. I don't know much beyond just the video that I saw.
Okay, so the questions are getting harder. So I think I will conclude with another hard question. Well, it's not precisely a question, but it's a discussion that's going on the IRC channel on Freenode. And I don't know, maybe you had an opinion on that. So there's ACE CVE on IRC that is asking, just curious, but would it be possible to make a garbage collecting allocator?
I think the answer is yes. I've actually seen one written by Jimmy. It was pretty old, and this was before I really understood memory allocation. So it looks like it's possible. I don't really know how it works because traditional garbage collectors require tracing, and we don't actually have a good way of tracing memory usage in our metadata space. Or like most manually managed memory spaces don't have a good way of tracing. I mean, it's possible we could build like a pseudo graph on top of that, but I don't really know how it works. But because one was written already, I'm inclined to say probably it's possible.
Okay, so some food for thought for the people watching. Well, that was awesome. Thank you, Benjamin. Is there anything else you want to say before we move to the break?
No, I think that was it.
Okay,
thank you very much.
I will say it for you. Make sure to check out his Twitch channel. That's twitch.tv/FengB. Is that correct?
Yes.
So make sure to watch and to ask him questions about memory allocation, WebAssembly, Game Boy emulators, and stuff like that. So thank you very much, Benjamin, again.
Thank you.
Okay, so now we are moving to the break.